Hydromet's mission is to observe, archive, and understand Guyana's weather and climate and provide meteorological, hydrological, and oceanographic services in support of Guyana's national needs and international obligations. The Hydrometeorological Service is attached to the Ministry of Agriculture. The department's general responsibility is to monitor and evaluate the weather and water resources in Guyana and to actively support the government in disaster risk management and aeronautical, water, agriculture, engineering, and other agencies for the socio-economic development of the country. It is the official provider of weather, water, and climate information and related products and services for Guyana. The collection of rainfall data began as early as the 19th century, but this was done here under the auspices of the various ministries and sugar estates. The Hydrometeorological Service was established on October 5, 1965, based on the recommendation of a World Meteorological Organization's representative. The service was once overseen by the Ministry of Works and Hydraulics, but then changed hands to the Ministry of Agriculture in 1992. Dr. Garvin.Cummings is the Deputy Chief Met Officer in charge of the Hydromet Service in Guyana.
The mandate of the Hydromet Service is very wide. The Water and Sewage Act of 2002 sets out our mandate to basically be the regulator of all of Guyana's water, whether those waters are atmospheric, surface, or ground. We are responsible for monitoring those waters, for archiving data on those waters, providing data and information with regard to the history and the future of those waters. So in that regard, we have several sections in the service that examines the different area or aspects of water. The National Weather Watch Center, which includes the aeronautical section and provides information for aviation, for the aviation sector, also provides short to medium-term weather forecasting. We also have a climatological section which deals with historical data and examining historical trends and being able to project seasonal variations in weather. There's the water resources section which deals particularly with surface and groundwater, that is our rivers and our aquifers. We have the Hydromet or agrometeorology section that deals with the applications of weather data and information to agricultural purposes. In addition to those sections, we also have the National Ozone Action Unit, which focuses basically on the Montreal Protocol and the phase out of ozone depleting substances.
For the most part, it is commonly believed that the Hydromet Service in Guyana is all about weather forecasting, but it also has a lot to do with hydrology or the management of Guyana's water resources, both above ground in our rivers, streams, and lakes, and underground in what is referred to as aquifers.
So the water resources section has two divisions. The first is the division that deals with surface waters, which includes all of our rivers and lakes. This type of information is important, especially for hydropower development and energy. Of course, we want to understand what is the energy potential of our rivers, what type of hydropower plant they can support. And in that regard, we have to constantly monitor the volume and velocity of the flows in these rivers. Part of the mandate of the Hydromet Service and the Hydrology or Water Resources section is also to include issues related to flood forecasting and disaster risk reduction. So we also have a dense monitoring network of the East Demerara Water Conservancy on all those rivers that flows along or into the coastal zone of Guyana, so that we can provide early warning with regard to fluvial flooding.
The work of the Hydromet Service is critical to several key sectors. Understandably, farmers are highly dependent on the data. Civil aviation depends on the information to advise on weather conditions in every part of Guyana. Local and international flights in and out of Guyana will not operate unless they are informed of weather over Guyana. The lives of passengers depend on the accuracy of this information coming out of Guyana's Met Service.
Like I said, the mandate is very, very wide. In terms of the Hydromet section, we're providing data here specifically for farmers. So you can think about cash crop farmers, livestock farmers, sugarcane farmers, rice farmers. But they also depend on the weather forecast that comes out of the climatology section and the National Weather Watch Center. The data that we provide as well in terms of rainfall data is also used for drainage and irrigation purposes. If you are going to design a drainage system, an irrigation system, you need to understand what type of, what amount of rainfall, what is the average, what is the long-term means, and so on, so that you can incorporate this into the design of such systems. The National Weather Watch Center, or the aeronautical section, provides data and information and forecasts for the aviation sector. We provide data for all aviation operators in Guyana, and this data is transmitted internationally as well for international air travel. So the data or the information that we provide is not only for local stakeholders, but we also have international stakeholders. The historical data that we provide is also used for climate change analysis. The daily observations that we do, they are assimilated into global models to provide forecasts for the different regions of the world, and that data is also used to provide forecasts for Guyana as well. So there's a whole broad spectrum of stakeholders that we provide data for.
So how do they do it? How does this department, with its 70 full-time staffers, read and interpret weather patterns, predicting weather, forecasting weather patterns over all of Guyana? I took my cameras to the weather station at Timeri, where I was given a walkthrough of the equipment used and how the data is interpreted. First, we took a look at the weather monitoring equipment in what is referred to as the Meteorological Observatory, an open square used to monitor various aspects of the weather. Walking us through this area is Mr. Aaron McPherson, weather forecaster at the station.
Okay, this square here is what we call the meteorological observatory. In the meteorological observatory, there are a number of instruments in which we use to measure different parameters. Say, for example, the temperatures. You have the sunshine, the amount of sunshine hours within a day. You have the rainfall, and also some wind information in terms of the direction and wind speed. As you can see, there are various instruments, and we will go into them as we go one by one to explain what each one is and what it is used for. Here, what we're going to look at now is what we call the Campbell-Stokes sunshine recorder. From this instrument, we record the amount of bright sunshine hours per the day. As you can see here, we have a spherical ball here, which is about 10 centimeters in diameter. And what happens is that when the sun would hit the ball, it would leave a marking on what we call, this here is a sunshine card. I have a sunshine card here, and on that is where it is born. Now the ball is like a magnifying lens. So as the sun tilts at a different angle during the course of the day, that's how you would know the burn. And then from this we can also know, like, for example, when we had a bright sunshine hours in the day, or when it was more of a cloudy day, or which period was a cloudy period in the day. Okay. Here what we are looking here at is at what we call the soil thermometers. Now each one of these soil thermometers is in a different depth in the soil. For example, this first one here is at 5 centimeters, the second is at 10, this third one is at 20, and the last one is at 30 centimeters. The purpose of this here is to measure the temperature of the soil at various depths. Say, for example, farmers will know like which soil is better for certain crops. Also, you can know the amount of water that would evaporate based on the temperatures of different soil. So farmers would like to have this information in order to know exactly whether the amount of water, if they need to water their plants more or use less water for the various plants based on the type of crop that they have. Here, this next instrument here we're looking at is what we call the evaporation pan. Inside the evaporation pan is what we call the still well, and here we have a hoe gauge. Now this here is used to measure the amount of water to evaporate it. If you look closely on here, on the hoe gauge, there are graduation, the measurements in which we record. So what happens, the still well, as the still well is there, as the name is the still well. So you don't want, like, say for example, now that the wind is blowing, the water is not stable, it is moving. So in the still well, the water is always at a constant level. So in order to do the reading, what we do, we simply twist this or adjust this to suit the level of the water. What happens, we look at it in terms of where the point of the hook just breaks the surface of the water. And we take that and then we do a recording. Now this here is being read at 8 in the morning and 2 in the afternoon. In order to calculate the amount of water that would evaporate within a day, you subtract the information that we would have today and tomorrow. In the cases where there is rainfall, you add the rainfall amount to the reading and to yesterday's reading, and you subtract to find out what is the information, what is the difference. Now the purpose of this here is for the example of you want to know where there is water being stored. You want to know how many water would evaporate within a day. Say for example, in terms of the conservancies, you want to know how much water would evaporate a day, so you can know whether the conservancy needs to add more water needs to be added to the conservancy or to be taken away from the conservancy. This here is what we call the 2 meters anemometer, and it what measures the speed of the wind actually. And what happens, as you notice it is on a rotating top. So as the wind hits the cups, it would rotate. And on here, if you look here, there are some readings here. So what happens when we record this information at 8 in the morning and at 2 in the afternoon, we use the information to calculate what was the speed of the wind between the period, over the 24-hour period. So sometimes you will notice, depending on the wind flow, you would have it going very fast or going very slow. Sometimes it is reversed, the spin is rotated. So it's all depending on the flow of the wind to determine how the measurement is taken. So here, as we move to this next instrument, this is what we call the Stevenson screen, or a common name as a thermometer house. Now, the design of the thermometer house is made in a special way, noting that it's off the ground. The purpose is that you want to allow the free flow of air to go under and over and even through it. Notice the vent-like look. That is the purpose of having it to go, the wind to blow smoothly through. Also, in addition to keeping it off the ground, we want to avoid it to any surface, say for example, any small plants or trees. You don't want that to affect the flow of the wind towards it. It is painted in white, and as it is to less reflective, less absorbent heat. So you don't want the color of it to affect the reading of the temperature. Now if we look here, inside the Stevenson screen, what we have 5 basic thermometers, and each one of them is recorded as a different thing. Say for the first one here, we have a maximum thermometer which gives us the highest temperature for the day. The highest temperature for the day is usually recorded at 2 in the afternoon. Then we have the minimum thermometer which refers to the lowest temperature of the day, and that is usually at 4 a.m. in the morning. Now here we have a dry bulb thermometer and a wet bulb thermometer. The dry bulb thermometer is to measure the dry air. You want to take out observing the effects of water being in it. And the wet one is where we factor in that water supply into it. The last one here, we have the grass minimum thermometer. The grass minimum thermometer is usually to measure the temperature at the top of the surface of it. Now here we have here attached a muslin wick. The muslin wick is the purpose of the muslin wick is to keep the thermometer always moist. Right? And notice each one of them are separated evenly, and some of them are tilted at an angle. The purpose of being tilted is that you don't want it to run back into the bulb of the thermometer. Okay, this here is what we call the manual rain gauge, and we have a number of stations around the country in which we have this here, and it is being recorded every day at 8 a.m. in the morning. That gives us a total a look of what would happen for the past 24 hours. Now meteorologically, you notice that I'm saying 8 a.m. every day. Now meteorologically, our day starts at 8 a.m. Now here, the rain gauge is also raised off the ground. The purpose is you don't want the surface of the earth to affect it. So what happens when the rain falls? It will fall in here into this funnel here, and it will go in our case we have a bottle in here. The purpose of the bottle is to just avoid it from seeping out to the edges or creases. You know, some things they might have a little creases or hole or it might corrode a bit. So you try to put the bottle to avoid it to seep out. You don't want any data to be lost. So what happens is we take the reading from the bottle and pour it into a measuring cylinder, and we record that information at each graduation. Now, inside here we have a number of containers. When the bottle would be filled, it would go into another container when there's excessive rainfall. So at no time you can see that there's any data being lost. So it goes from one into another. If this one fills, it goes to the next, and if this one fills, it goes into the last one here. So basically that is our manual. And this here is around the country. We have it at, say some examples, we have it at Cameron, we have it at Kaichor, we have it at Lethem. There is even one in the Botanical Gardens. There is one in Anna Regina. There is one in number 53, Beachboro Bees, and so. So there are a number of stations across the country that have this manual rain gauge, and that is to help us to monitor the rainfall pattern around the different areas.
Inside the weather station, the data gathered from the observatory is analyzed and interpreted for communication to all stakeholders. The station is also responsible for weather forecasts, as is explained by Station Chief Meteorologist Lyndon Alves.
After the observation is done, the observer comes into the office and records the information on our register page. This contains all the elements: the temperature, the pressure, wind speed, direction, cloud amounts, cloud heights, and all the other parameters that they would have observed outside. And then a message is created, a message known as a METAR is created and transmitted to the airport using this system up here. Now, another part of our duties is to transmit this data to what is known as the GTS, the Global Telecommunication System. The GTS collects data from all of the stations worldwide, puts it in one place, and then uses that data to calculate the forecast. The forecast is calculated using weather prediction models. They're just equations and parameters that describes how the weather evolves in time and space. For example, this chart that you're seeing here, this is a calculated forecast. What you're looking at here is the wind speed and direction seen by the barbs, and the green, the different shades of green, that is the relative humidity at the different heights over Georgetown in this case. This is what it is expected to be for the rest of the week, from today, Thursday, to next week, Wednesday, the 25th of November.
What is that telling you right now?
In this case, it is showing us that this is known as the mid-level, From the middle to the upper levels, we are seeing a generally westerly wind with a lot of moisture. And in the lower level, relatively high moisture, but not as high as the upper level, and we have easterly wind. Now, this information is used by the forecast to determine the probability of having deep convection or just light showers. In this case, we are seeing that you have something that is known as a trough right here in this general area. You have what is known as a trough at the upper level. So any little system, any little perturbation at the lower levels could result in deep convection over Georgetown for the rest of the week, at least until Sunday, which coincides with the forecast that we would have issued up to this morning. For the next couple of days, we're expecting mostly cloudy to overcast conditions with showers and possible thunder showers over at least the northern part of Guyana. Now, to see how this looks in real life, let's have a look at just about here. It's saying 12Z, so we're seeing that there's a lot of moisture in the entire column over Georgetown, and this will be representative in today's case, of the entire coastal belt. We have a little perturbation that passed us this morning, and you have a lot of moisture in the column. So that is reflected presently by what we're seeing here. This is the radar image. We're seeing that you have a line straight along the coast. You have one here, and then you have another one here. So right now this would be just to the south of Georgetown along, let's say you're coming on the east bank. This would be just about Friendship, Land Canaan, that area. So we're seeing here that they're having, or they would have had some showers in the last 15 minutes. In the case of Timeri, we had a light shower. You saw the observation time, we had a light shower. So that would have passed, and this line is coming towards us. So that is showing that with the moisture and the little forcing that we have in the lower level and the support of the upper level, it produced this feature that we're seeing, a line of convective clouds and accompanying precipitation. In the case of this model, this data is calculated at a space of approximately 60 miles. Every 60 miles a calculation is done for the different parameters. Now with a space of 60 miles, you cannot find systems that might be smaller than 60 miles in length. So what is done at this office? We have a system in the corner, a computer in the corner, that takes this data and does a recalculation. It recalculates it to a smaller distance. In this case, you're looking at here is 15 kilometer space. So we take approximately 110 kilometers and we break it down to 15 kilometers. So this is what we use in the office to look for smaller systems. Things that you would not be able to see, or you wouldn't be able to see it as well using the data that this system would provide us with. In this case, you're looking at precipitation, and at least in Guyana's case, no precipitation is forecasted for this period of 12 hours. This is another tool that is used by the forecaster to do a forecast and to also have a look and continuously monitor the weather. What we're looking at here is a satellite image. In this case, it is what is known as an IR image, stands for infrared radiation. So what we're looking at here is the height at the tops of the cloud. We can see in this area we have a large area of disturbed weather. This is associated with a system that is called a trough that is approaching, a tropical wave, that is approaching Guyana. In our case, we could see the line of clouds that are seen at the top here. They're now beginning to be visible on the image, on the satellite image at the bottom there. You could see them as these different shades of white and mauve or pink, whatever color that is. Another satellite image is the visible image. Now this looks like a black and white photograph taken by the satellite, and in this case we're also seeing the area of disturbed weather, and we could also see over Guyana the cloudy conditions that we have over the coast and for most of the country, well, except for this part of Region 9. When it's looped, we could see the progression of the clouds, which would correspond to the progression of the whatever system is approaching. So you can see in this case you have, because of the winds at the upper level, you have these clouds coming in the opposite direction. This is a visible image, so during the night it would always show up as black. So you could actually see the difference between day and night. So as the sun rises, then we start to see the clouds over Guyana.
A Doppler radar is a specialized radar that uses the Doppler effect to produce velocity data about objects at a distance. It does this by bouncing a microwave signal off a desired target and analyzing how the object's motion has altered the frequency of the returned signal. This variation gives direct and highly accurate measurements of the radial component of a target's velocity relative to the radar. Doppler radars are used in aviation, sounding satellites, meteorology, police speed guns, radiology, and healthcare. Partly because of its common use by television meteorologists in on-air weather reporting, the specific term Doppler radar has erroneously become popular with the use of radar used in meteorology. Most modern weather radars use the pulse Doppler technique to examine the motion of precipitation, but it is only part of the processing of their data. So while these radars use a highly specialized form of a Doppler radar, the term is much broader in its meaning and its applications. The Doppler radar in use at the weather station at Temari is a critical component of the Hydromet's ability to forecast patterns and systems. Mr. Romain Coum is the telecommunications and electronics engineer at Hydromet.
Here we have the Doppler weather radar, what it looks like inside. Up in the dome, we can't go up there, but there's an 8.5-meter dish that is spinning at a high velocity and radiating electromagnetic wave. So the radar system is made up of basically 4 parts, which is the antenna unit upstairs. We have a transmitter unit, the receiver unit, and the control unit. So the whole process starts here. There's a magnetron in here that will generate a microwave. This microwave will be sent up in this tube up here and be guided straight to the antenna, and there it is sent out into the atmosphere. This wave, when it hits anything in the atmosphere like raindrops, clouds or so, it will be reflected, and the reflected wave will come through the same guide and come into the receiver. In the receiver, it is pre-processed, further processed, and sent to the forecaster downstairs where you are seeing the images for the interpretation. The system is controlled over here because it's an integrated system. There's a lot of different systems came together to make this possible. So all the controls happen on this end. And just to put into perspective, this little carrier you see here, this is the GDRX, which is the main processor. This little carrier is $11 million. Just to do so. Alright. And to come over this side, well, to keep power going, we have some UPS, some massive UPS here in the case of failure from GPL. So this will keep it running until our automatic generator kicks in to keep it running. In here, the temperature is always kept cool by AC is running all the time. And there's a little dehumidifier in here, which is going to keep moisture out of this waveguide that I was explaining earlier, because if there's moisture in there, when this creates its electromagnetic wave, it can cause arcing and we can have an explosion. So this has to be on at all time, even when the radar is off. Yes, to check the status of the radar, it can be visualized in a little visual program here that you can have an idea that everything is okay right now because it's in green. If something is wrong, automatically it will be shown up in red, and we can go in and find out more about the parameters, what's wrong and what's right.
Before leaving the weather station, Station Chief Lyndon Alves walked us through some of the exhibits on display on the long climb to the Doppler system control room.
This is just some old equipment that was used before. In this case, well, they are both rain gauge. This one is what is known as a recording rain gauge. It contains something like this over here. A drum, a spinning drum with a chart on it that would move something like the ECG. So it would show you the amount of rainfall in time. So from that you could calculate rainfall rates, how much rainfall you had in a specific period. This here is the conventional rain gauge that gives you the rain. It just gives you the rainfall. It doesn't tell you how hard it was falling. It was light or heavy, over the case may be. On this chart, you just have some instruments: your thermometer, wet and dry bulb, your maximum and minimum thermometer, your barometers, both Android, recording and a normal barometer. This is also, these two are also barometers. This is the digital barometer. This is what we are using mostly these days, since mercury is prohibited. The use of mercury is prohibited. And the wind vane. We have what is known as the wind socks and your conventional wind vane. Over here we have an anemometer. This gives you the wind speed. You would have seen one outside in the plots. And over here, yet another barometer. This one records. There's a clock in the system that turns this drum. And again, there's a pencil that would draw a line, a continuous line, that would give you the pressure at different times in the day. This instrument is a water level recorder. It is used not in meteorology but in hydrology. It is used to follow the height of the water in, whether it be your rivers, your streams, the conservancy. This works. You have what is known as a weight and float. This goes on this wheel here. When this wheel moves, it has a pencil on the other end that writes on this chart. This is the clock mechanism that causes this paper to move continuously, whilst the pencil would draw a continuous line on the paper. This instrument, and also this one here, this is used to determine how fast your river is flowing. This is submerged in the water, and this cable is connected to an instrument. Now, as these cups turn, it would interrupt a signal that is in the head, and that counts along with a clock to give you how fast the stream or the river flows in a specific location.
Why is it important to know that?
This is important if you're, well, most of our hydrological studies with rivers, they're geared at assisting Guyana to one day reach the potential of generating electricity using the rivers. In other words, having hydropower in Guyana.
A critical component of the Hydromet service is its National Ozone Action Unit, or NAOU. This unit is tasked with responsibility for coordinating and monitoring all activities towards the smooth phase-out of man-made ozone-depleting substances, or ODS, in Guyana. This is in keeping with Guyana's commitments under the Vienna Convention for the Protection of the Ozone Layer and the Montreal Protocol on Substances that Deplete the Ozone Layer. These agreements were acceded to in 1993. Guyana subsequently ratified the London Amendment, Copenhagen Amendment, and the Montreal Amendment in July 1999. Guyana was identified as a low-volume consumer, or LVC, and as an Article 5 country, with the assistance of the Multilateral Fund, or MLF, through its implementing agency, the United Nations Environment Program, and the Regional Office for Latin America and the Caribbean. The approved country program was formalized. This provided the basis for the designated focal point for the Montreal Protocol, the Ministry of Agriculture, Hydrometeorological Service, to establish the National Ozone Action Unit. The NOAU-HYMS is responsible for coordinating and monitoring all activities towards the smooth phase-out of man-made ozone-depleting substances in Guyana. Ms. Bianca Day is the National Ozone Officer within the National Ozone Action Unit.
Now, the Vienna Convention on the Protection of the Ozone Layer and the Montreal Protocol on Substances that Deplete the Ozone Layer are two very important international agreements. The National Ozone Action Unit is a unit within Guyana that is responsible for monitoring the importation and the use of substances that are classified as ozone depleting substances. Now, our main stakeholders being the persons that work within the refrigeration and air conditioning sector, as well as the Guyana Revenue Authority, which plays a very major role in monitoring importation of these substances. And well, the National Ozone Action Unit, two trade orders were passed. The trade order number 19 of 2007, and this was for the phasing out of CFCs, or chlorofluorocarbons, and then it was amended in 2010 to include substances that are HCFCs, or hydrochlorofluorocarbons. Now, Guyana was able to phase out CFCs 2 years before the scheduled time, which was 2010, and we phased it out in 2008. So these substances can no longer legally be imported into the country. And we're currently working on phasing out HCFCs, which should be completed by 2040. However, we completed the first phase of our HBMP, or HCFC phase out management plan, and stakeholders, they've agreed for Guyana to have an accelerated phase out. So we're looking to have these substances completely phased out in Guyana by 2025. Now, how the phase out works, on an annual basis, we have a quota system, which is the maximum allowable amount that could be imported for the year. Now, importers would register with the unit, and then the quota is shared among them, and they cannot exceed their quota for any given year. This is published in the official gazette on or before January 15th of each year. Well, we are in constant contact with persons within the refrigeration and air conditioning sector. Now, there is a ban on HCFC, equipment containing R22 gas, so they cannot be imported into the country, while the gas is still allowed to be imported, just for servicing of equipment that's already in the country. Now, we're looking at greener technologies. Currently, we are looking at the R410A gas, which works under high pressure, but it's much more ozone friendly, as well as friendly global warming. Potential is very low, so that's one of the alternatives that we're looking at. There is the option of going to use hydrocarbons, and there are some safety concerns, so we're currently working to have a standard developed on the handling, use and transport of hydrocarbons before we make that transition to using that. However, it is used by some technicians locally, but we're trying to get that safety measure in place before we fully buy into that technology.
According to the deputy head of the Hydromet service, Dr. Cummings, the data recorded over the last decade shows distinct changes in rainfall patterns, both in terms of intensity and timing as it relates to the two seasons.
Locally, what we've been observing in terms of weather, we have seen that there's an increase in short duration, high intensity rainfall events. In other words, there are some months, for example, where you might have the first 20-25 days of the month being relatively dry, but you may have just one or two 24-hour period, or even less, of very intense rainfall that causes that month to surpass its long-term average. And in fact, those very, very intense rainfall events can create localized flooding. In some cases in Guyana, some regions have been flooded because of these rainfall events. In addition to that, we are currently now having a preliminary study being done in terms of where we're examining the shifting of the rainfall season, the primary rainfall season, as we call it in Guyana, the May-June rain, which we have been observing is shifting more towards July. In other words, most of the rainfall is going later into the rainfall season. So July is becoming apparently a wetter month than it used to be historically. We've also seen, because we're in an El Nino phase now, we've seen also increases in temperatures as well. but this also fits in well with the global averages in terms of temperature increase as well. So these are the type of effects that one would anticipate would come along with climate change or long-term climate variability.
The Hydromet's weather forecasts have been the butt of many a joke in Guyana. Sometimes one is listening to a weather forecast that declares sunshine, but outside it's pouring. More recently, forecasted El Nino conditions that are expected to last until May of 2016 was ridiculed as being inaccurate. But according to Dr. Cummings, weather forecasts are often misinterpreted by the ordinary man in the street.
One of the challenges that we've got at Hydromet is public perception of what the service does and the accuracy of our weather forecasting. The challenges, well, one of the challenges that we have with weather forecasting, not only locally, but globally, is how do you make global scale models applicable to local or to community level activities. Most of the models that we deal with have very low resolution. So it is very difficult to give point forecasts. For example, in 1 square kilometer, what would happen in terms of Georgetown. For example, on a global model, Georgetown is just a point on the model. And how do you forecast for a point? So the forecasts that we generally issue are for all of Guyana. And sometimes we may forecast rain, for example, in Region 4. This does not mean that all of Region 4 will experience rain. Parts of Region 4 might have rain, the other part might not have rain. But this does not mean that the forecast was inaccurate. So we try to give forecasts that are more general because we don't have the resources locally, or I would even argue regionally, and probably even internationally, to give point forecasts. That sort of forecasting is what we can only be done if you have a very dense network of radars. And the communication system must be significantly improved in order to communicate those forecasts with a very, very short time period or lead time. Unfortunately, we don't have that type of resources. We have one radar to cover a very large country. In other places, you have weather updates on the television or on the radio every half an hour. In the case of Guyana, we can only do that maybe every 4 or 5 or 6 hours. So it becomes a greater challenge as well to provide that sort of forecast. The next issue is that we don't have observers all across Guyana. We can only provide observational data where the population is because of the nature of the network. So there are many locations where we don't have people living. We can't have rain gauges because there's nobody there to observe, to record the data. What we've been investing in the last 5 to 10 years are much more automatic or automated stations that can self-record the weather. The challenge with these systems is that they depend heavily on cellular coverage for data transmission. In the case of Guyana, most of Guyana, well, not most, but a significant part of Guyana is not covered by cell signals, so it's difficult to have these stations transmit back to our forecasting center if we don't have cell coverage. We can also use satellite transmission as well, but because of the dense forest cover and cloud cover, it's difficult to have accurate data transmitted that we can use in our forecasting system. But having said that, we have a good bunch of young forecasters who are highly motivated, excited about the job, and are willing to learn. So once we can keep these persons on the job, because a significant part of weather forecasting is experience. If we can keep them on the job for sufficiently long, then we anticipate that our weather forecasting could only improve with time.
The term El Nino conditions is often misunderstood to mean a drought, but according to Dr. Cummings, the El Nino conditions being forecasted in Guyana basically means that there will be a significant reduction in rainfall quantities, and not the absence of rainfall altogether, as may be implied by drought.